Hi everyone, and welcome to the last video of the Combinatorics topic. This is the fourth video of the Combinatorics topic as part of the Year 11 Mathematics Specialist Year 11 curriculum. I'm introducing combinations last, even though it's something that you deal with in methods, because I think the way that I've introduced permutations first and then gone over a couple of counting principles is a bit more useful for understanding combinations on a bit more of a theoretical and abstract level. And the formula will hopefully make a little bit more sense now more than it did when you studied it in methods. So this is something that you deal with in methods, but you go into it at a bit greater level of depth and mathematical rigor than you do in the Year 11 methods course. So in terms of the unit outline, I'm obviously going to reintroduce the concept of combinations, even though I've done that in my previous video on combinations in the Year 11 methods course. So if you haven't seen that, make sure you check that out. But anyway, I'll be going over it again. So I'll go over what the n represents in this formula, what the r represents, what these two notations are, that they mean the exact same thing essentially, but they're just two ways of saying the same thing. I'll then be going over some problems involving combinations. So I'm actually going to do this point first and then this point. So problems involving combinations, what I mean by that is I'm going to look at some basic combinations problems, and then I'm going to look at some more complex combinations problems and some problems that actually involve both combinations and permutations. There are certain cases where you need to choose objects first and then you need to arrange them. So that's where you might deal with combinations and permutations in the same question. And they're obviously a bit more difficult to problem. Then the next thing I'm going to have a look at is Pascal's triangle. We also do go over Pascal's triangle in Year 11 methods, but again, you go over it to a bit more of a depth. You go into proofs and proving certain results within Pascal's triangle. And I'm going to go over some of those proofs and some of the properties of Pascal's triangle, which are a bit important. And which you might actually face in a test or exam as well, in a Year 11 specialist test or exam. So let's get straight into the video. Okay, so first of all, in terms of what a combination is, combinations are essentially selections, like permutations are, except in this case, our order does not matter. So they are selections made regardless of order. And since we've introduced permutations as being n factorial divided by n minus r factorial, it'll be a bit easier to understand how we derive the combinations formula. N choose r is equal to n factorial over r factorial and take r factorial. So in this case, we can see that the only difference between the permutations formula and the combinations formula is that we divide by an r factorial. This is the arrangements of objects we have chosen. So essentially what the combinations formula does is it's the same as the permutations formula, except we divide out the order, the arrangements, because in the case of combinations, we don't care about the arrangements. All right, another way of writing combinations is as n choose r in a vertical column notation. This is equivalent to n choose r. Here, what the n represents is the number of objects we have to choose from. The objects we can choose from. And r represents the number of objects we choose in each selection. The number of objects in each selection. So let's say we are trying to choose two unique objects out of the set of objects A, B, C, D, E. In this case, our n is equal to 5 and our r is equal to 2, giving us 5 choose 2, which is equal to 10. Now, combinations problems can be relatively basic and they can be relatively straightforward. A basic example of a combinations problem is, like I indicated before, choosing two objects from 5 objects. Another case we might choose is maybe we have a group of 6 students and we want to select 2 students. In this case, the order doesn't matter again, so we use combinations. 6, choose 2, and in this case, that's going to be equal to 15. Maybe in another case, we want to select 4 students. In this case, that's equal to 6 choose 4. And this, if we plug that into our calculator, is equal also to 15. This is not by coincidence, because choosing 2 students is the same as not choosing 4 students. So each choice we make when it comes to combinations actually is 2 choices. We are consciously choosing one set of students, and we are not choosing the other set of students. This results in the more general algebraic sort of property of combinations that n choose r is equal to n choose n minus r. We can prove this by considering the formula for combinations. The right-hand side, in this case, is equal to n choose n minus r, which is equal to n factorial over n take r factorial, multiplied by n take r factorial. If we simplify this, we get n factorial over n take r factorial, multiplied by n take n plus r factorial, giving us, finally, n factorial over r factorial, n take r factorial, which in this case is equal to n choose r, the left-hand side. Some other important notes that we should mention is that n choose 0 is equal to 1, since there is only one way of choosing 0 objects. And also that n choose n, given my formula here, is also equal to 1, because there's only one way we can select all of our objects. Furthermore, n choose 1 is equal to n, since all of the selections are where we select each individual object, and due to our formula again, n choose n minus 1 is also equal to n. Now we might deal with some more complex combinations questions. For example, if we have restrictions on the number of choices we can make. So combinations with restrictions. The other thing I'll talk about is combinations from multiple groups, and I'll go over that afterwards. So when it comes to combinations with restrictions, what we want to do is we want to deal with the restrictions first. Okay, and so what that entails, for example, let's say we have 7 people, and let's say we have a group of 7 workers, let's say, and we want to create a subcommittee of workers who make decisions for that group in a union meeting, for example. And let's say Grace is one of the workers, and Grace must be in the committee. Maybe they've decided she's got the leadership potential that's necessary to be a part of this group. Now, our restriction in this case is that Grace must be in the group. And so what we want to do is we want to deal with this restriction first. Remember that we are trying to choose 4 people. Our group is 7, our n is equal to 7, and in this case, our r is equal to 4. However, we additionally have this restriction of Grace having to be in the team. Therefore, we have one Grace out of the 7, and we must choose that Grace. The next case involves selecting from the remaining 6 workers the other 3 places. And so the total number of subcommittees that can be formed, including Grace, is equal to 1 choose 1 times 6 choose 3. Now, let's say we have a case where people can't be in the same group. In this case, we kind of deal with the complement. When we deal with the complement, we consider the total number of cases that are possible without any restrictions, and then subtract the case that we don't want. Let's say we have 8 students, and there are 2 students, Sam and Rick, who don't get along and they can't be in the same group together. In this case, what we do is we first consider the total number of cases that we can have and subtract the cases where Sam and Rick are both in the same group. In the first case, let's say we want to select a group of 4 students. So again, in this case, our n is equal to 8 and our r is equal to 4. So our total number of possible cases without any restrictions is going to be equal to 8. Choose 4. However, we don't want Sam and Rick being in the same group. To consider the case where Sam and Rick are in the same group, we consider Sam and Rick, choose both of them, and then we fill the remaining 2 positions in the group from the other 6 students. And so the number of cases where Sam and Rick are not in the same group is equal to the total number of cases minus the cases where they are in the same group. We might also deal with combinations with choices from multiple groups. Let's say we have a group of 7 men and 5 women. And we want to form a subcommittee that comprises of at least, let's say 3 men and 2 women. Okay? In this case, we are selecting from multiple groups. We are selecting from the 7 men to choose 3, and we are selecting from the 5 women to choose 2. Let's consider another case. Let's say we have to make a subcommittee that is equal to a total of 5 people, and it must have at least 1 woman. In this case, we can consider, again, the complement, in the same way we considered the case with Sam and Rick. In this case, we consider all the possible selections that we have, and we subtract the case where there are no women in the group. The total number of selections we can have with no restrictions is equal to 12 choose 5, summing the number of men and women together. Then we subtract the case where no women are in the group. This would be equal to no women being chosen, and out of the 7 men, 5 men being chosen. As a result, this is equal to the number of cases where at least 1 woman is in the subcommittee. This next case I'm going to consider is where we combine combinations and permutations into one question. There are some cases where we need to make a selection first and then arrange that selection. One case might be, let's say we have the letters of the word riffraff. And we want to determine the number of possible arrangements, of possible 4-letter arrangements. Now, we can't simply do, 8 permute with 4. The reason why we can't do this is because we have 4 Fs and we have 2 Rs, which are identical, and thus rearranging those letters won't change anything. Instead, we need to consider a series of mutually exclusive cases. The first case is where we choose 4 Fs. In this case, we only have one way of arranging them because we have 4 different Fs. They are all identical, so there is no difference if we arrange them in any different way. If I look at riffraff, just for reference, and write it like this, I can see that I have 4 repetitions of Rs. The second case we might have is where we have 3 Fs and 1 unique letter. In this case, I have, again, in terms of my Fs, I have any number of any of them I can choose. There's only one way of selecting the 3 Fs because there's no difference between selecting one F from another. And then, in terms of the 1 unique letter, I can select from R, I, and A. So I have 3 possible options. So I have 3 choose 1 possibilities. Then, in terms of arranging them, I have 3 Fs, 1 unique letter. So I have 4 factorial divided by 3 factorial different ways of arranging that. This is the number of Fs, the number of repeated units, so I divide out those arrangements. The third case involves 2 Fs and 1, 2 unique. Sorry, I don't know why this is bolded. So in this case, there is one way of selecting those 2 Fs. Again, I'm selecting from R, I's, and A's. So I have 3, choose 2. And then I multiply this by, sorry, that should be a multiplication symbol there. And then I multiply this by 4 factorial over 2 factorial. The fourth case would be equally where I have 2 R's and 2 unique letters. In this case, there is one way of selecting those R's. Again, 3 choose 2 ways, because in this case, I have a I, F, or A that I can select from. I can't select 2 F's in this case because I have 2 unique letters in this case. So I multiply that by 4 factorial over 2 factorial. Another case is where I have 2 F's and 2 R's. In this case, there's one way of selecting those F's, one way of selecting those R's, and I have 4 factorial over 2 factorial, 2 factorial arrangements. The sixth and final case is where I have all unique letters, R, I, F, and A. Thus, for unique, that is equal to 4 choose 2 times 4 factorial ways of arranging them. And to determine the total number of arrangements, of 4-letter arrangements, taken from the letters riff-raff, I sum all of these mutually exclusive cases. The final step and final point from this unit is Pascal's triangle. Now, Pascal's triangle is something you might have seen before. It's this triangle where each of the corresponding 2 terms above sum to form the next term. 1 plus 1 in this case is equal to 2, for example. 1, 3, 3, 1, and so on and so forth. Now, what's actually the case is that a Pascal's triangle is equal to 0, choose 0. Then the next one is 0, choose 1, 1, choose 1, 2, choose 0, 2, choose 1, 2, choose 2, and so on and so forth. Okay? And as a result, we generally tend to call the first sort of row equal to n is equal to 0, then n is equal to 1, n is equal to 2. So note that the first row is the n equals 0 row. In terms of the columns, we denote this first column, r is equal to 0. This next column, r is equal to 1, r is equal to 2, and so on and so forth, because it corresponds to that value there. R is 1 is this one, R is 0 is this one. Correspondingly, the n's, in this case n is equal to 0, corresponds to this value, n is equal to 1 corresponds to these values, n equals 2 corresponds to these values. This also leads us to the conclusion that n choose r is equal to n minus 1 choose r minus 1 plus n minus 1 choose r. Okay, and that's because of the fact that in the Pascal's triangle, each of the corresponding values, each of these values is equal to the sum of the 2 values directly above it. We can also prove this mathematically. I will leave that up to you to do. Another of the properties that Pascal's triangle shows is that n choose r is equal to n choose n minus r. If we look at the symmetry of Pascal's triangle, the one on the leftmost side is equal to the one on the rightmost side. This is a property that we've already proved, and we can use the formula of combinations to equally prove this property here. As a note, it's easier to start from the right-hand side and work your way to the left-hand side. Okay, I think that's everything from the combinations topic. If there is anything I've missed, make sure you do alert me in the comment section. If you have any questions or anything that I haven't gone over in enough detail, make sure you let me know and I'll upload some supplementary content. Otherwise, that's it for this video and I'll see you in the next one. Thanks, guys.